Okay, let's take one more very important step forward, particularly from a mathematical perspective of describing a wave. So far, we have used some very elementary and elegant notions of high school physics and math, if I may say so, which is sinusoidal functions of trigonometry, which we know so well, right? So the electric field of the light wave was essentially written down here as not exponent, sorry, repeat. Let us now take, sorry, repeat. Let us now take an important step forward in our mathematical description of the wave and the solution to the wave equation in one dimension for light fields. The electric field of the light wave, we wrote this down as E of xt equals the constant amplitude A multiplying cosine of kx minus omega t minus again the constant initial phase or absolute phase of theta, right? Now we take a sort of little leap forward as we would have done when we first learned the notion of the complex exponential function, exponent of I phi, where I is the unit imaginary number or the square root of minus 1, and phi once again is the argument to the trigonometric cosine or sine function. This is the phase. So we know this identity very well, that e to the I phi or e or exponent of I phi is equal to cosine phi plus I multiplying sine of phi. Therefore, we can also now very nicely write down e of xt using the real part of exponent of I phi, which is cosine phi, to be e of xt is equal to the real part of a multiplying the complex exponential function exponent of I multiplying kx minus omega t minus a theta, right? Now, mathematically, this description has many advantages, so we are going to stick to this a lot from here on. But then the real part of a complex number is nothing but one half the same complex number taken and summed up with its complex conjugate, right? So the most popular way of writing the whole thing down, that is in this case the one dimensional description of the electric field E of xt, to be a half a exponent of I kx minus omega t minus theta plus the complex conjugate written with the abbreviation cc. So let us get used to this and um, etch this in our minds, as we are going to use this quite a lot in this course to follow, right? So what is particularly important or useful for this course, and that is the following, right? So using the complex notation for waves has the particular advantage of the following. Pause here. Well, using the complex notation to describe the electric field of the wave has particular advantages, and we have particularly used this form of writing the electric field in terms of the uh, complex valued function a, which is equal to the exponent of I kx minus omega t minus a theta, right? Earlier I had, in the previous view graph, we had essentially defined e of x comma t to be the following. It is 1 half a multiplied to the complex exponential function with kx minus omega t minus theta in the argument plus cc, which is the complex conjugate. This is tantamount to the real part of this complex quantity a exponent I kx minus omega t minus theta, right? So this is the most accurate way of writing everything down, because electric fields are real fields, real valued vector fields, something which I will stress and emphasize in subsequent lecture sessions too. But then, while this is the case, mathematicians, physicists, and engineers look for some degree of convenience. So, with a slight abuse of notation, what we do is the following. We take the electric field E of xt, but use a tilde underneath or on top of E to emphasize the fact that this quantity can be complex valued, although electric fields are real valued functions, and write things down in the following way. We write the electric field E tilde of xt to be a exponent I multiplying kx minus omega t minus theta. We don't bother to explicitly write re or real every time. Okay, this is maybe an advanced user's habit if you wish, but then it makes a whole lot of math and equations compact. But then this goes along with the understanding that we know very well that electric fields are real quantities, and it's for the sake of math that we write down E tilde to be what it is. And in any case, whatever we do with, play around with the symbols and do all our calculus and algebra, and when we arrive at a result, we should just remind ourselves that what matters in terms of a physical quantity is simply the real part of the result. Okay, so let us upgrade ourselves to this somewhat advanced habit and use E tilde of xt to be the quantity of relevance here to describe the electric field. E of xt is a exponent I kx minus omega t minus theta. In other words, we can also now write this down in the following way. We separate in writing down E tilde of xt a, the real valued amplitude of the wave, and then multiply this with the other constant factor in this expression, which is the polar part, a part of the polar side of the complex number, that is exponent of minus I theta. Theta is again independent of xt, and leave this iconic exponent of I kx minus omega t, which is reminiscent of the x minus vt form, aside, right? And this is a nice way of separating out the amplitude part and this exponent of I kx minus omega t, which is responsible for the propagation of the wave and carrying it through, right? So we have separated the constants from the stuff that is rapidly changing, right? Now this allows us the luxury of defining a so-called complex amplitude of the wave to go hand in hand with the real amplitude of the real valued electric field function as follows. E naught of tilde on the left hand side is complex valued, and its polar form is essentially a, the amplitude, multiplied by the exponent of minus I theta, where theta is the phase or the polar coordinate of this complex number, right? Therefore, we can now very compactly write E tilde of xt to be E naught exponent of I kx minus omega t. So exponent of I is of course the complex exponential function. As written in this case, the field appears to be complex, but once again I should emphasize that electric fields are real. Electric fields can be measured in a laboratory. The corresponding potential differences can also be measured, just as we have on every wall plug that is beside us very likely at the moment, right? So now in order for us to keep track of whether we mean a complex electric field amplitude or real, one should in literature be meticulous enough to put the tilde and do it, but it's possible that in some pieces of literature this is even left out. So it is then the business of the user, the reader, the researcher, or the advanced learner, as could be in this case, to keep in mind that these notations hold sway in optics and electromagnetics literature and interpret them accordingly with the knowledge of what is essentially captured in this important view graph, which we hope will also be um, referenced frequently by the learners and instructors in this course. Okay, why did we take pains to go through with this defining this complex notation for electromagnetic waves and optical waves, particularly using the electric fields as we have done? The reason for this is that the complex number way of writing it, or the complex notation being used here, the complex exponential function replacing real trigonometric functions cosine and sine, has tremendous advantages, because optics is all about waves sort of adding up to each other and so on and so forth, as we will see. And adding waves, especially of the same frequency but different amplitudes and with different absolute phases, can, for example, become extremely easy and almost trivial in terms of computing the math out in this case. So this could have been significantly more cumbersome had we used trigonometric functions, but with exponentials this is easy. So let's consider a scenario where we need to sum up three waves, 1, 2, and 3, with particular complex amplitudes E1 tilde, E2 tilde, and E3 tilde, with the fact going together with this that these three waves have the same frequency, angular frequency, cyclical frequency, or frequency, which is omega here, and omega here. So omega of 1 is omega, omega of 2 is omega, omega of wave 3 is also omega, right? Because the omegas are the same and we are considering the case of one-dimensional propagating waves, if they are in the same medium, the velocity also turns out to be the same. Therefore, the magnitude of the propagation vector k also turns out to be the same. So the omegas and k's in all these three cases are the same. Of course, this is not the most general scenario. We are considering this just for an example. But then E1 of tilde, E2 of tilde, and E3 of tilde need not be identical. If we consider this instructive example, then in the case of using the complex notation, look at what happens. Now this is a multiplication of two complex valued functions, E1 of tilde multiplying the complex exponential function with kx minus omega t in its argument, right? So then we use the linearity in multiplying and adding complex numbers and simply write the sum as the sum of E1 tilde plus E2 tilde plus E3 tilde as the coefficient to a common exponent of I kx minus omega t. Right? Actually, if you just jog your memory a little back and now consider the scenario where we had E1 cos kx minus omega t minus a theta 1, E2 cos kx minus omega t minus a theta 2, E3 cos kx minus omega t minus a theta 3, you immediately realize that the math would not have been as simple as looking at the first equation and simply writing down the sum almost instantaneously, right? So that's really the convenience and sort of power of complex numbers being used in describing these waves, although electric fields are real. One can easily imagine that we can continue adding any number of waves, for example, which share the same frequency and propagate through the same medium, and writing out their sum would be an almost trivial exercise, right? the point also to note here is that the absolute phases or the initial phases need not be identical in this case, right? The initial phase of the wave 1 theta 1, initial phase of wave 2 theta 2, and initial phase of wave 3, that's theta 3, could well be different. Now let's just look at this graphically. So let's take wave E1. This is wave E1. Its amplitude variation in either x or t. This is just a two-dimensional plot. So let's consider either x or t one at a time. Then take wave 2. Now the snapshot of the amplitude variation of wave 2 has just appeared. Note for a fact that the frequencies of cyclical or angular frequencies of these two waves are the same. So the nus are the same for both the waves. If I look at it from the perspective of time, or the lambdas of these two waves are the same if I look at it from the perspective of the spatial variable x. So take E3 also. Each of these independently can be described as E1, the cosine of kx minus omega t minus a theta 1, E2, cosine of kx minus omega t minus a theta 2, E3 multiplied by the cosine of kx minus omega t minus a theta 3. And the fact that the amplitude maxima are offset by some amount tells me that theta 1, theta 2 and theta 3 are different. They are not all identically equal to each other. They are all, these waves have some offsets or delays as the case may be, right? But then the complex notation very nicely captures the sum of all these three waves, which is also another electric field, right? This is also another complex or total electric field, E tot, as we have written down here. We will, in the specific case of light waves, show very clearly that we can superpose waves and add them up in a medium. In fact, for a student of physics or engineering, this may not be a surprise at all. Why? Because the wave equation, as we had written it down earlier, which had the following form, and I recall, this equation in its entirety, in every term in this equation, is linear. Therefore, this linear superposition of independent individual solutions to this equation should also automatically be a solution. The sum E total of these three waves is denoted by this thick blue line, which is this. Let's move on now